What is going on, guys? Welcome back to my channel and welcome to my sixth video. In today's video we're going to be talking about the EEPROM and how to basically create a virtual EEPROM so we can have persistent settings and memory that stick around even when we turn the device off. So the main way that we're going to accomplish this on STM32, because this particular line of microcontroller doesn't embed a native EEPROM. Like, it doesn't have an EEPROM that is designed and built into the hardware. So what we have to do actually is take advantage of the flash memory. And the flash memory is where all the program is stored. So when you compile the program and it gets sent to the microcontroller, basically what it does is it erases the flash and it reprograms the flash with the instructions that are inside your program. And that's good because even when you turn off your device and you turn it back on, the code is still there. You want your device to be able to turn on and off and still have the code that you flashed it with. It would be really annoying if every time your microcontroller turned off, you had to reflash the entire thing. So we can see over here on the right, this PDF, that the flash section of the microcontroller is broken up into different sectors. This is different from what some people might be used to, because a lot of other microcontrollers, I think like F0 up to F3 or F4, uses pages. And the pages are kind of broken down into smaller chunks of the flash memory. But for the high performance microcontrollers for STM32, they're going to be broken up into sectors like this. In this case, we have 8 sectors, 0 through 7, and the total flash size is 512 kilobytes, but each sector is a varying length. So you can see sector 0 is only 16 kilobytes, and then they gradually increase in size up to sectors 5 through 7 or 128 kilobytes, and that's how it goes. So when we flash our program, the flash is actually going to be stored starting in sector 0, and that's actually defined over here in our linker file. And I'm not too familiar with linker files, but I can kind of go into them if people are interested. But essentially, what this says is that the flash section starts at address 0x8000000, and the length is 384 kilobytes. So when you guys start and create your project using the Cube IDE or the Cube MX, what this file is going to say is it's not going to have this line. It's just going to have this and 512 kilobytes, because the entire flash memory is dedicated to flash settings. But what we have to do here is we actually have to partition the flash into the flash and the EEPROM. So we're going to have only 384 kilobytes, 512 minus 128, and then 128 for EEPROM. So the way that we're going to organize is we're going to use sector 7 as the EEPROM section over here. So we're going to have 128 kilobytes dedicated for EEPROM. And this is a little bit overkill, just because there's no way that I'm going to have 128 kilobytes of data that I need to be stored on this thing. That's just like way over how much I have. I think my EEPROM is really only like maybe 100 or 200 bytes of data. So this is a little bit too much, but my program size itself is much smaller than any of this. So if you have a program that's over 500 kilobytes and you really are pressed for space, then what you could do is you could have your EEPROM go into sector 0, which only takes up 16 kilobytes, and then have the rest of your program go from address 0x8004000 all the way till the end, and that'll kind of save you on space. But since I'm not really pressed for space right now, I'm just going to push it to the end in sector 7. And then if we come down here, we see we're also going to have to add this line. And I'm going to be totally honest, I'm not sure exactly what this line does. This is all stuff that I kind of took from other people, but it's going to be this line. Basically says the EEPROM section is at 0x08000, 0x08060000, and yeah, I'm not going to try to explain this. I'm going to do more research on linker files just so I can have a better understanding of this, and I can maybe do another video. But I'll put a link in the description to a video that does a better job at explaining linker files. What we also need to add to make sure that this works is this variable right here called constant uint8_t attribute section dot EEPROM used EEPROM array, and then the size of the array. So not super familiar with this, but I'm going to try to explain it through this what I did some research on. So basically what the section does is it allows you to create these sections that map to special hardware. So, section attribute straight from gcc.gnu.org. The section attribute specifies that a variable or function lives in a particular section. So what we're doing right here is we're saying that this .EEPROM, which is the section that we created in the linker script, is reserved for this data EEPROM array. And this EEPROM array variable isn't actually used, but it's basically saying that we want to partition a certain amount of data into this section. And the size of this array is going to be 131,072 bytes, which is equivalent to the size of 128 kilobytes. Remember, a kilobyte is not exactly 1,000 bytes, it's a 1,024 bytes. So it's a little bit of some weird conversions here. So that's going to be the size of the array. This basically ensures that this section is used for what we want it to. And now that we have that, we now have our EEPROM correctly partitioned off so that we can use it for our own use. So the main functions that we're going to be running through here are all in the config.c file. So if you open up my GitHub, you can pull all the code from the config.c, which I don't think is inside the folder. I think it's just inside the src folder. And there's a few functions that we're going to have. We're going to have read EEPROM, write EEPROM, and then our last function is check first time, which essentially what it does is if there's nothing inside the EEPROM, so say it's a blank microcontroller, there's nothing in it at all, then it's going to check to see if there's anything in it. So it checks if it's a new EEPROM configuration, and if it's new, there's nothing there, then it's going to write it with the default settings. So there's like scale factors for the MCU, different kind of PID parameters, cutoffs, like for the yaw rate scalings, all those different parameters are going to be written in as the default values. If, however, it's not a new configuration file and it already has the settings in it, then it will only rewrite to defaults if you tell it to do. So if you check first time true, then regardless of what's in here, it's going to write defaults. If it's false, if you put false here, then it's going to check to see, hey, has this already been written? Okay, it has been written. I'm not going to rewrite it because you don't want to rewrite it if it's already been written. So the first function that we're going to look at is read EEPROM. And this starts with this variable EEPROM config, which actually exists in main.c. And EEPROM config is a variable that is of type EEPROM config underscore t, which we're going to go into now. So this is a structure that holds all of the data that we want to be stored into the EEPROM. So random calibration settings, there's PID parameters, and then other just random stuff that helps with the drone, stuff that we want to be persistent when it turns off. So this structure contains all the data. And we create this variable, EEPROM config, which stores all of the EEPROM data. So if at any point you're debugging your code and you want to see what the value is of the EEPROM, you can always check this variable right here. So what we're going to do is we're going to start off by creating this variable DST, which is an uptype EEPROM config underscore t, and is a pointer to the address of EEPROM config. So basically saying, okay, whatever's over here, put into this variable DST. And then now DST, since we want to read from the EEPROM, the values in DST are now going to be whatever exists at address of the start of the EEPROM. So at 0x08060000, whatever exists there, we're going to put it into DST, and we're going to format it according to this struct, EEPROM config underscore t. Sorry about all the stuff popping up. So that's how we're basically going to take all the EEPROM data and put it into this variable DST. And since DST is a pointer to EEPROM config will now contain everything that existed in a memory address of sector 7 over here. So everything over here is basically being put into this value EEPROM config, and that's how we're going to read. Pretty simple operation. Write EEPROM is a little bit more difficult, simply because if you want to write a variable to any other like RAM address, it's pretty easy. You just kind of create a pointer to the address space, and then you can put a value there. But for the flash memory, it doesn't allow you to simply just like take stuff in and out of there all willy-nilly. There's lots of protection to the flash, and this also comes from the fact that you want flash. Some people who are creating closed source programs don't want flash to be read, because if you have a program that you don't want other people to see the source code for, then you want to have protection on it. So there's all sorts of different ways to read and write from the EEPROM, and it's a little bit more difficult than normal variables. So we create this variable called erase of type flash erase underscore t, and I'm going to show you what that looks like right now. So essentially what this structure contains is the type of the erase. So there's two types of erase that we can do. We can do either mass erase or sector erase. So we can either erase every single sector at once, or we can pick a sector to erase. And then we choose what sector we want. We choose the number of sectors. So this is the starting sector. And then we can choose the voltage range. So as we saw in our last video, when we were going over the reset and clock controller, our voltage range is voltage range 3 because we are from 2.7 volts to 3.3 volts, and this is going to be shown up here. 2.7 to 3.6 is our voltage range, so we're in voltage range 3. So if we go back to our file and we look at erase dot type of erase, we're going to do erase sectors. Number of sectors is just going to be 1 because it's just one sector 7, sector 7, and the voltage range 3. So now we're going to create two variables, the source and the destination. So since we're writing, we want to write from a source to another location. So we're writing from our source is going to be whatever is stored in EEPROM configs. Remember, EEPROM config is our variable that contains all of the settings. So we want to write from our source EEPROM config to the destination, which is going to start at the flash starting address, or the sector 7 starting address over here. So from source to destination. And then the first thing we have to do in the flash cycle is we have to unlock it first. So unlocking it is going to be shown over here. So first we have to unlock it, and we have to write these keys to the flash key register. So essentially you take key 1 and key 2, and you start by writing that to the flash key register over here. So if it's locked, you see right here, if it's locked, then write key 1, write key 2, and then verify that the flash is now unlocked. If it's still locked, then this function did not work. Otherwise, it did work. Return true. So that's the first thing we're going to do, is we're going to have to unlock the flash. So yeah, it says over here, after reset, write is not allowed in the flash control register to protect the flash memory against possible unwanted operations. For example, electric disturbances. Okay, so lots of different uses over here. Then what we're going to have to do, so first we unlock it, then we have to erase it. So you can't just write to a single byte inside of a sector. You have to erase the entire sector and then reprogram the whole sector after that. So what we first have to do is we have to erase their sector based on the parameters that we put in up here. So flash erase, and then, so the first thing we have to do is we're going to see over here, to erase a sector, is first we want to check that no ongoing operation is going on. So we have this function called flash wait for last operation, which basically waits for the busy flag to be not set, so it's no longer busy. And then there's all these other things that basically clear flags and ensure that no other weird error stuff happened. So it goes through that, and then once it returns true, we can pop out to over here. So what we now want to do is, if our erase type is mass erase, then we're going to do the flash mass erase. Remember, this is a setting that we initialized over here. So in our case, we have type erase sector, so it's not mass erase. But just in case you want to do a mass erase, I'm going to go over this file, this function as well. So flash mass erase basically takes in the voltage range. So for us, that's voltage range 3. And then you can see over here on the right, in the reference manual, it's going to show you exactly how to do. So check that there's no operation ongoing. We already did that above. Set the MER bit, the mass erase bit, then click set the start bit to include the voltage range, and then wait for the busy to be cleared. So in my case, I don't wait for busy to be cleared, but it still works regardless over here. So flash mass erased. Sorry, actually, I do wait for it to be clear. That's my bad. Up here, after we do the mass erase, wait for the last operation, and then pop out of there. So if it's not a mass erase, then it's going to be erased by sectors. In this case, we're going to start with the first sector up until the number of sectors that are to be erased, and we're going to erase sectors one by one. So in our case, we only have one sector, sector 7, and the number of sectors is 1, so it's only going to run through this once. So when we go to do the sector erase, what we do is we put in the sector that we want to erase, and then the voltage range. So when that goes to here, basically if the voltage range is voltage range 3, then our flash P size is word size. and you'll see how that comes in over here. So basically, if you look over here, we have the program size. Program size is 32 bits. So p size word is 0x2 pushed over 8 times. So you can see that's 2 pushed over 8. And then we write that into the CR register over here, temp size. Then we unmask it, and then we say sector erase, put the sector erase bit in, and then the SNB is the sector number, so that was sector 7, so we put that over here, and then we do the start, so that'll start the operation that we want to do. And then after that, we wait for the operation, and then if it's completed, then disable these 2 bits, and then we're good to go. And then if we want to erase multiple sectors, then it's going to go up and loop through and erase all those sectors. So now that we've erased the flash memory, what we're going to now want to do is program it with what we want. So we can essentially only program the flash one either word, byte, or half word at a time. So byte would be obviously 8 bits, half word 16 bits, and then word would be 32 bits. So we can only program it in those increments. So we create this variable, EEPROM config number of words, and this variable number of words is the size of the struct in bytes. So however many bytes are in the struct, and then divided by the size of uint32_t, which is 4. So basically we're taking the bytes, divide by 4 to figure out how many words there are inside this struct. And we go over here and then we program it word by word. So flash program from the destination, from the source to the destination, we're going to want to program. So what this function looks like is first we wait for the busy flag to be set over here, and we can see what this actually looks like over here as well in the reference manual. So this is the programming sequence. So check that there's no ongoing operations. Then we go over to flash program word, and we're going to pass the address and then the data. And then so we set the PG bit. We also have to ensure that it's it is formatted to word size. And then now it's just a simple write operation where we basically take a pointer to the address, and all we have to do is we've got to put in the data. That easy. Put in the address and then the data. And that will essentially put into the spot in memory that we want to write to the data that we're trying to write. And we're going to go through and we're going to loop through every single word in the config file. Sorry, we're going to loop, and what we're going to do is we're going to loop through every single word in the config struct and put that into the destination. And then so after we program, we're going to wait for the operation to be finished. And I'm not sure if this is essential, but basically we also clear the PG bit as well afterwards to make it ready for use next time. So we're going to go through, and that's how we're going to program every single thing into it. And then after that, we have to lock the flash. And then now what we're going to do is to ensure that the data is actually set there, we're going to read the EEPROM settings. So back up here to reading, we're going to read into config_EEPROM_config whatever exists in the flash memory. And this should be a redundant operation because essentially what we just did was we wrote into the flash memory whatever was here. But now to make sure that it actually worked, we're going to read from it back into the config file. And this should do nothing, but it's a good way to check to make sure that the flash operation actually worked. And that is going to be essentially the whole operation over here. So we write EEPROM, and then it goes through the bottom, and then we have some stuff that just ensures. So I do want to touch on this function check first time, which basically makes sure that we don't write new settings to the EEPROM, or we don't write default settings to the EEPROM if it already has old settings from a previous run. And how this works is the first variable in EEPROM config is going to be this variable version. And on default, version is set to an arbitrary number. In this case, I have it set to this check new EEPROM conf, which is 29. So by default, this variable check new EEPROM conf, which goes into version, should be 29. And what it does, so I'm trying to find the file, down here. What it does is essentially it reads in whatever is in the flash memory, the first byte. It reads the first byte of the flash memory into this value called test val. And if test val is not equal to 29, then it knows that there's bad data in there, or essentially the flash has been overridden back to its default. So if the flash is overridden back to its default, then the first value in the sector is not going to be 29. So now we know, okay, we actually have to put in the default values. So if the first value is not 29, or even if it is 29, but we actually set this to true and we want to reset the system, then it will go through all of this. So there's two ways that we set the default. If the first value is 29, meaning that it was already previously written to, or if we tell it to reset. And that's gonna be the way that we go through and set all the default settings. So that is going to do it for this video. Thank you guys for sticking around. This is definitely a bit of a longer one, so I apologize for that. But I think it's all pretty good information. Next video, I think we're gonna go into some of the serial stuff, so probably UART and talking on to just basically how to set up UART over DMA, and how we're gonna use that to do debugging and other sorts of logging for the drone. Thanks for sticking around, and I'll see you next time.